Here are the answers to the test on atomic structure. You would have had one of the first two questions, and they're kind of asking the same thing. Which of the following charges could not have been observed on an oil droplet in Millikan's oil droplet experiment? And so we know the charge on one electron. It's even given to you in the question, and it's given to you in the AP packet. And so the accumulation of charge on the outside of an oil droplet has to come in whole number quantities of that. And so it could not be negative 2.6 times 10 to the negative 19th, or it could not be negative 2 times 10 to the negative 19th. It has to be some whole number quantity of that, negative 1.6 times 10 to the negative 19th. So for example, like both of them, the second choice is negative 3.2 times 10 to the negative 19th. So that would be an oil droplet that accumulated 2 negative electrons. The second question, we'll get into some of this more when we do bonding, but we kind of mentioned that different types of radiation can cause different changes to a particle. Microwaves are low energy waves, and so they cause a pretty low impact change to a particle. We just make molecules rotate a little bit. We make bonds rotate, and eventually we'll see that more when we build Lewis structures and like ball and stick models that you can twist and turn, like little ball and stick models. You might have even used those last year with those little model kits. You can twist and turn the bonds. And so it's like a pretty mild change because it's low energy. No bonds are broken. The structure of the particle is not changed in any way, nor are the properties. Infrared radiation is a little bit more energetic, and it causes molecules to vibrate, or even bonds to start to vibrate, which that can lead to a potential chemical change if the vibrations become strong enough. And then even more energy would be into the visible light or the ultraviolet light portion of the electromagnetic spectrum. And so these are higher energy waves, so they're going to cause a little more drastic change to the particle. And this is where we see electrons transition up and down the energy levels. And so I think about flame testing, that when you flame test, you see, light waves in the visible light portion of the spectrum. And it doesn't mean that there aren't ultraviolet rays given off. There definitely are. We can't see those, but if I burn a piece of copper in a flame, I can see the green color. Well, then I know that we're absorbing energy and then releasing that energy when the electrons fall back down to the ground state. So it's visible light and ultraviolet light that start to cause electrons to transition. That's the amount of energy the electron is gaining to move up the energy levels. That's the amount of energy released when the electron falls back down. So when it says oxygen molecules absorb ultraviolet light but not visible, hydrogen molecules absorb both visible and ultraviolet. Which of the following statements is true? Well, first, when they're talking about ultraviolet and visible light, and these are the types of light that they're mentioning, it's got to be something about electron transitions. And really, then there's only one choice. It's got to be the first one, right? That ultraviolet light would be more energetic than visible light. It's beyond violet, visible light. And so more energy is required to cause electrons to transition in oxygen atoms versus hydrogen atoms. So that was kind of the way to make this question a little more manageable, is just to catch that they're mentioning ultraviolet and visible, and then to know that, oh, yep, those are the types of energies that I see when electrons are transitioning amongst the energy levels. Most of them here were good. You either had a question that said which transition would result in the release of the most energy, or which would require the most energy. If energy is being released, then the electron needs to be falling from a high level to a low level. So the biggest transition, high level to low level, should be B. If I'm adding energy, then the electron should be jumping up the energy levels. So here the largest transition up the levels is D, level 1 up to level 5. So that was kind of the key with those. You had one of the two, and we had to just catch, well, what direction is the electron moving? Are we gaining energy or losing energy? And then most of us did fine with the orbital diagram for phosphorus. We just have to be careful when we have 3 electrons in p orbitals. They should be distributed amongst separate p orbitals. That minimizes repulsion. If I'm ever asked, it's to minimize repulsion. The reason why the last one would be wrong is because when there are 2 electrons together in an orbital, they must spin the opposite. That kind of helps to relieve some of that repulsion. The excited state, you would have had one of these two. The excited state should just have an electron that's up in a higher orbital or a higher energy level than we would expect. So, for example, in the first one, I really shouldn't be up here in the second energy level until I completely fill the 1s. Kind of similar to the second one. If I only have 1 electron, it shouldn't be in the 2s, it should be in the 1s. Now, if I were asked to identify these elements, the first element is an excited form of lithium, and the second element is excited hydrogen. The number of arrows or the number of electrons will identify the atom, but I can tell that they're both excited because they're not in the correct filling order. Paramagnetic would mean that I'm attracted to a magnet, and there are unpaired electrons. So paramagnetic, unpaired electrons. Dimagnetic would mean the electrons are all paired, di meaning 2. And so it might help to think about either orbital diagrams or electron configurations. I mean, obviously, the noble gases here would all have full orbitals, so I'm kind of just looking for the outer orbitals or the outer valence shell. And so if I have 2 electrons in an s orbital, or if I have 10 electrons in a d orbital, I know they're full. Or if I would have had anything that ended in something p6, that's full p orbitals. So I know here, like magnesium, these are full. These are all full. S2, D10, those are all full. Now obviously here with chromium, the 4s2 is full. Even though this is an even number, 3d4, when I think about the d orbitals, there are 5. So let's say these are my 3d orbitals, and I fill them 1 electron at a time. Oh, so yeah, they would be unpaired. I think sometimes people get kind of confused because they'll be like, but it's an even number. Yeah, it's an even number, but you have to be careful with the d's. There are 5 d orbitals. So if I only have 4 d electrons, they are all getting their own orbital. Which would be kind of similar with manganese. Manganese would have been the answer to the second question. You would have had one of them. And all of these S's are filled with 2. In zinc, the D is filled with 10. But in manganese, I would have 5 d electrons. And so each electron gets its own orbital. And now even if I had copper with 3d9, there will be 1 singular electron, but manganese has 5. So it's most attracted to the magnet. It'll have the most unpaired electrons. Because now obviously if I have 9d electrons, now I go back and pair them. There would still be 1 unpaired electron, but manganese for the win. Manganese would have 5. Which of the following electron configurations is correct? I kind of highlighted things that were incorrect. So gallium, that should be the 3D. In bismuth, after the 5D, I should go back to the 6P. If I were doing a noble gas shortcut for calcium, I'd have to use the previous noble gas, which should be argon. But bromine is right. Argon, 4s2, 3d10, 4p5. The other option would have had gallium, incorrect. Again, that should be the 3D in the middle. The bismuth is correct. That should end 6p3. The calcium again is wrong, because if I'm going to use argon, then the next orbital should be the 4s for 2. And the bromine is wrong again. It should be the 4p. And yes, there are 7 valence electrons, but it should end 4p5. The other 2 valence electrons would be in the 4s. All right, then this one was fine. This one with a formula of element Z and fluorine. No major issues with this one. You could have just figured out what element it was, and maybe that helped a little bit by adding up the total number of electrons or just looking at the last orbital. The first option would have been indium, number 49, and the second was tin, number 50. It helps then in maybe identifying the valence electrons, which you could either do just by looking at the periodic table now, once you know where the element is located, or you can add up the valence electrons using the configuration. Valence electrons are the electrons in the highest energy level. That includes anything here in the 5th energy level, the 5s and the 5p. So indium has 3 valence and tin has 4. If I'm going to bond them with fluorine, I know fluorine is a -1, and then I can write my formula. Now, it wasn't a choice with this tin one, but here's something kind of interesting. We say that like the transition metals, tin and lead, can have multiple charges, and so often then when you see formulas with transition metals, tin and lead, you see Roman numerals to indicate what charge is being used. Well, here's kind of what happens with tin, and lead for that matter. We usually say that tin and lead can either go +2 or +4. They're the most common charges. Well, if I lose all 4 valence electrons, then you can kind of see what would happen, right? We would lose the 5s2 and the 5p2. There'd be 4 valence electrons, we would just lose all 4. And that would create a very stable configuration. But another stable configuration is if we were to just lose these guys. If tin were to just lose the 5p2, that would create a +2 ion. And then I do have full orbitals. Oh, which would be relatively stable for tin. Now, obviously, the other option is to go +4 and lose all 4 valence electrons. But that's kind of what happens with some of these transition metals, where sometimes there can be multiple ways of getting a relatively stable configuration. And that's what happens with tin and lead. They can either lose 2, just the 5p, and then we're down to full orbitals, or we can just lose all 4 valence. But obviously then like a Z +2 ion, which could happen, like tin could be +2. Thankfully, that was not one of the choices. Okay, so then this was one of the questions that was more commonly missed. The configuration of a manganese or an iron ion. So you would have had one of these. This is like an AP concept. I wouldn't give this to a first-year kid. I might have a first-year kid do a configuration for like a sodium ion. We do that. But we don't get into transition metals. With transition metal ions, I mean, number one, they're always positive. All metals will form positive ions, but you lose the outermost electrons first. The outermost electrons, especially here, like with manganese and iron, the outermost electrons are these guys, the 4s2, and it'll be like that for any transition metal. That the s electrons are a little farther from the nucleus, so maybe they're filled previously, but they're in a bigger orbital, so they're farther from the nucleus. And when we talk about removing electrons, we want to remove the electrons that are farthest from the nucleus first, because they're farthest from that positive core. They're going to be the least attracted to the positive nucleus. The first two to go are always those 4s. Now, if it's manganese, then that's it. In the case here, manganese plus 2, done. We would lose those 4s2. They're farthest from the nucleus, so it should end with just the 3d5. Oh. Most common boo-boo is to end it like 3d3, where you at least know that plus 2 means to lose 2 electrons, but you just took off the wrong 2 electrons. We want the 2 that are farthest from the nucleus. Now, similar with iron, iron forms a stable plus 2 ion. It can lose just the 4s2. Here's the other common form of iron. Iron's most common charges are plus 2 or plus 3. We can either lose just the 4s2, they're farthest from the nucleus, or now if we lose one more, I would be losing the D, and I would go to 3d5. But do you know what's kind of special about 3d5? Everybody's got their own orbital, right? If I have 3d6, there's 2 electrons sharing, and that'll have a little repulsion. But if I go 3d5, now all the d orbitals are filled with 1 electron. And so you can kind of understand then that, oh yeah, I could see why iron could either go plus 2 or plus 3. We could just lose the outer electrons, the 4s2, because they're farthest from the nucleus. Or we could lose that extra d electron so that all the orbitals only have 1 electron and no repulsion. Tricky. Valence electrons, outermost energy level, not just the last orbital. All the electrons in the highest energy level are my valence. And then finally, there were 2 different options for the free response. So obviously if you didn't have this one on sodium, you can fast forward it to potassium. They were both very similar. Now, just an FYI, often we don't even think about reading the directions, but the directions do say to show work for all your calculations. So if you just have an answer, you get nothing, because it doesn't show that you understood how to arrive at that answer. And maybe you are just a wacky genius, but then prove it. It also says to pay attention to significant figures. We want to make sure that all of our final numerical answers are reported with proper sig figs and units. In question A, we want the configuration of a sodium atom and a sodium ion. The atom has 11 electrons. The plus 1 ion should have 10. Compounds of sodium produce an orange-colored flame when heated. And so you can see that with a flame test, or if you electrocute a pickle, you can see that too, right? Orange light with a wavelength of 625 nanometers has a frequency of, well, eventually I want to use the equation speed of light equals frequency and wavelength. But you have to be careful with your units, right? When you use the speed of light, it's in meters per second. But I have a wavelength in nanometers. So I need to convert that. Unless you want to convert the speed of light into nanometers per second, you could do that. But you got to make sure your units jive. So now I've got meters per second, and then I've got my wavelength in meters. And we can just solve for the frequency. The units on the frequency should be like 1 over second, seconds to the negative first, something like that. And 3 sig figs. The original measured wavelength, the 625, that had 3 sig figs. So we can leave 3. Then in part C, we want to calculate the energy in joules of 1 photon. This one's plug and chug, right? You got the equation in your packet. E, energy of a photon, is Planck's constant times the frequency, which we just calculated. So if you made a boo-boo with your frequency calculation, but then you plugged it into the equation for energy properly, you would obviously lose for part B. but you can still get full credit for part C if you used your frequency properly. And this should come out in joules because Planck's constant is in joules. And I went 3 sig figs again. So now this is the joules per photon. This is the energy of 1 photon of orange light. Okay, so now part D starts to get into ionization energy, which we're going to talk about now in the second part of this unit. Ionization energy is the energy required to remove an electron, to ionize the sodium atom, to remove this outer electron. So we've talked about what it means to form an ion. Well, if electrons are negative and the nucleus is positive, there's attraction there. So we're going to have to add energy to remove an electron. It's called ionization energy. It's often measured in units of kilojoules per mole. So a student proposes the idea that the orange flame is because orange light consists of photons that have the energy needed to ionize the sodium atoms. So is the energy of the orange flame, is it ionizing the sodium atoms? Is it enough to remove the electrons? Is the student's proposal valid? Justify with a calculation. So all we have to do is compare these energy terms. So it takes 495 kilojoules per mole to remove electrons from sodium atoms. Orange light has an energy of about 3 times 10 to the negative 19th joules per photon. Well, we just need to make sure that these units match so that we can compare them properly. So it doesn't really matter which you wanted to change, as long as in the end you got the units to be the same. So I took my energy of orange light and changed it from units of joules per photon to kilojoules per mole. And so eventually I had to switch the joules to kilojoules, and then per photon to per mole. And then I got about 191 kilojoules per mole. So that would be the energy of orange light, a mole of photons, which could then ionize a mole of sodium atoms. Or could they? Invalid! No, they could not. So if I had like a mole of orange photons, I would have 191 kilojoules of energy. But that's not enough to ionize sodium atoms. It takes like more than twice as much energy to ionize a mole of sodium atoms. So no, this orange light is not removing electrons from the sodium atoms. We're not ionizing the sodium. In fact, we're just exciting the electrons. The orange energy causes the electrons to move up and down the energy levels, and I'm adding 191 kilojoules to get the electrons to move up the energy levels, which then we're releasing 191 kilojoules when the electrons fall back down, and then I see the orange light. But the electrons are not being removed from the atom. They're just being excited and moving up to higher energy levels, but they're not being totally removed from the atom. Orange light would not be enough energy to ionize the atoms. Fantastic. Now, if you didn't have the potassium, here's another example, one that you could practice, or if you didn't have the sodium, you could practice the sodium. Really similar. Sodium burns with an orange flame. Potassium gives us a violet or purple flame. We wanted the configuration of a potassium ion, still +1, so we'd be removing that last electron to form the +1 ion. They give me the wavelength of violet light as 415 nanometers. But before I can use the speed of light, I need to switch that to meters. So that meters and meters jive, right? So I've got my wavelength turned into meters. I've got the speed of light. I can calculate the frequency in units of, again, 1/2 seconds, seconds to the -1st, The 415 was 3 sig figs, so I left 3 sig figs. And then in part C, I can use that frequency along with Planck's constant to solve for the energy of 1 photon of violet light. About 4.79 times 10 to the negative 19th joules per 1 photon. Cool. So a lot of this was plug and chug, just making sure that my units matched up, right? This does come out right away in joules because Planck's constant is in joules. Then again, ionization energy is the energy required to remove an electron, to ionize the potassium atom, to remove that outer 4s electron. It takes 419 kilojoules to remove a mole of electrons. Or say a mole of electrons, or say 1 electron per mole of potassium atoms. It would be a mole of electrons. But I've got energy now per photon of this violet light in units of joules per photon, and I need the units to match. So yeah, it doesn't matter which you want to change as long as you can get them the same. So I went with the kilojoules per mole. Let's get them both in kilojoules per mole. So I switched my joules to kilojoules, did some dimensional analysis. I had joules per photon, which then I put the photon on the top, per mole on the bottom, 6.022 times 10 to the 23rd of anything in 1 mole. And I got about 288 kilojoules per mole. Fantastic. So this is the amount of energy that was added or absorbed by these potassium electrons. It was also the amount of energy released when the potassium electrons fell back down to the ground state. That's why we see the violet light. But that, again, is not enough energy to ionize a potassium atom. All that energy does is make electrons move up to higher energy levels, which is not stable, so they eventually fall back down, release that energy as the violet light. But it's not enough energy to totally remove the electron. That would require 419 kilojoules per mole. So the violet light only excites the electrons, but it's not enough to totally remove them from the atom.